regardless of which group they are. Use the halogens, fluorine, bromine, iodine, or chlorine, or from that paradigm, attach a nitro group, which is electronic chlorine. Then that increases the ability, and that's essentially an electronic that we use. And in a similar way, another type of reaction is formation of cyanohydride. Which also converts an sp2 hybridized carbon to an sp3 hybridized carbon, just like the hydration. And the way this reaction progresses is that you need to have cyanide as the nucleophile. As we have already seen in chapter 8, cyanide is a good nucleophile. But typically, hydrogen cyanide is not very good for this purpose because it is a weak acid. So not enough cyanide is present. Normally, the reaction is carried out with a salt, like sodium cyanide or potassium cyanide. So in the first step, what we want to do, and let me just give you a real example. Let's say you have acetaldehyde. And then in the very first step, you use sodium cyanide or potassium cyanide, means that the cyanide is negatively charged. That attacks the carbonate group. As we have seen, the carbonate has a small amount of negative charge in the oxygen and a small positive charge on the carbon. Therefore, the cyanide attacks the carbon, forming the tetrahedral intermediate. So the hybridization changes from sp2 to sp3 in this very state. So it changes to that. In the subsequent state, you just provide the acid, which can be used for this purpose, HCl or any other, or H2SO4, which protonates. Therefore, this one picks up the proton going to the cyanohydride. So this is therefore a two-step process, which is, you can do this reaction with hydrogen cyanide, but the reaction does not progress very well. In that case, it's much slower because not enough CN minus is present there. So this is the ideal way to carry out hydrogen. And again, we see a similar trend here in terms of how this reaction works. If we look at the various types of aldehydes and ketones, starting from, let's say, acetone, which is much slower reaction, and the K value in this case is about 14. If you go to acetaldehyde, which is the one we just showed, this is immediately jumps to about 1,000-fold. K is greater than 1,000. And if you go to formaldehyde, this goes to about 100,000. So there's a clear-cut evidence here also that the aldehydes work better than ketones unless you change the group in the ketone where you have an electron withdrawing group. Similar to the hydration properties, you will also see an enhancement of the rates for those kind of situations for cyanohydride formation. So in theory, therefore, this follows the same trend. Now, one of the importance of the cyanohydride formation is that you not only change the sp2 hybridized carbon to sp3, but also you generate a new carbon-carbon bond. So cyanohydrides can be converted to other products, as we'll see later. If you treat either an aldehyde or a ketone with an alcohol under acidic condition, that's important. So you provide a catalytic amount of acid in there. They can form initially what we call a heavy acetal. The heavy acetal has one hydroxyl group, and another one is the OR prime, which comes from the alcohol. Okay, and I'm just indicating different R groups. There's some of them could be the same, but essentially different alkene groups shown here. Now the heavy acetal undergoes another reaction, generating what we call an acetal, where the OH should be replaced with OR prime. So this is called an acetal. So now let's try this reaction with something that we already know, some common aldehydes and ketones and a particular alcohol. So let's say we start with acetaldehyde again. And we treat it with ethanol. In the presence of an acid, HCl or H2SO4, for example, catalytic amount that can catalyze the reaction, generating ultimately an acetal that will have the formula as such. You have CH3 connected to OCH2 CH3 and OCH2 CH3. Obviously, it goes through a heavy acetal intermediate. So this is the acetal that is being formed. So how this reaction progresses, we can actually follow it, and it has very good similarity with the hydration. Yes.
You start it over.
So the acetal usually goes through formation of the heavy acetal. So let's follow the reaction. If we start with acetaldehyde here, and we provide catalytic amount of the acid, let's say we have H3O plus. The very first step is transferring one of the protons to the oxygen. So first step is transferring the proton to the oxygen. So this is what is formed in the first step. And this can react with the ethanol that we provided as the solvent. And of course, this can be written into two resonance forms. One is this, the other one would be where the positive charge would be on the oxygen. So this is a resonance hybrid of these two forms. And you can do the reaction with either one, directly on the carbon, or if you attack this carbon, the electron migrates if we do the reaction this way. performed in the first reaction with one molecule of ethanol, this proton can be transferred. Either another alcohol moiety can pick up that, giving you the hemiacetal. So it forms the hemiacetal. So the hemiacetal again can undergo another reaction where this can be protonated. So the subsequent step involves protonation of the oxygen of the hydroxyl group by, again, let's say the acid. So the protonation happens here, giving you this. And now you have very good living group, the water molecule in, and that can happen by donation of the electron pair from oxygen, giving you plus water. So this would be form which can undergo a reaction with the second molecule of ethanol. Which generates the
You can do a video if you want. I can give a video if you want. Oh, yeah.
little problem, but you can see because it involves a lot of steps. But I'm trying to show you that the steps are fairly straightforward. As you can see, you protonate the oxygen, then you eliminate the molecule after that by attack of the alcohol moiety. That generates the protonated species, which then transfers the proton. There's the hemiacetal. The hemiacetal undergoes the same kind of reaction subsequently by elimination of a molecule of water and then being attacked by the second molecule of ethanol. And then again, this hydrogen would be removed by a second molecule of ethanol, and you get acetal. Right? So you can figure this out. So these reactions are therefore reasonably straightforward in terms of how the reaction proceeds step by step. As long as you have acid present, you can catalyze this reaction and make that. Now, one interesting thing is that you can also make cyclic acetal. So, if you have a molecule such as this, let's assume that you have a molecule like this, which has both the carbonyl group and the alcohol in the same molecule. And then you can anticipate a reaction between the two different moieties of this. Okay, you expect this reaction to go the following way, that this would be protonated by initially so the acid, let's say, transfers the proton, right? So we generate this. Now it can be internally attacked by the OH group here. Forming in the subsequent state, you have another molecule of the alcohol pick up this proton, giving you cyclic heavy acetal. So it is possible to have an internal reaction within the two parts of the molecule, one alcoholic group and the aldehyde or ketone group in the molecule. It is also possible to have two reactions generating from the same molecule. So another example is using an ethylene glycol. Let's say you have this reacting with ethylene glycol with lithium acid. And you are familiar with ethylene glycol. It's actually the green stuff in your car, which is used as an antifreeze. So ethylene glycol. And in that case, now, there are two alcohol units, and therefore what you expect to see is a cyclic acetal, which would be so this is a cyclic acetal. So essentially you carried out two reactions with both OH groups of the same molecule and generate this, which is this is the CH2CH2 unit in there. So this is a cyclic acetal that is being formed, and these reactions are reversible. So you can also acidify that and regenerate that aldehyde or ketone that is formed. So you can carry out the reverse reaction using the acid. And the thing, of course, is that this process generates water molecules, right? So if you have excess water, it's going to go to the other side. And so the reaction can be manipulated accordingly. If you use a relatively dry acid, it's going to force the reaction to go to the acetal, and the acetal can be hydrolyzed in the presence of aqueous acid. And that's why these reactions are often used for protecting the ketone groups in some of the reactions. Protecting group means that you can carry out the reaction in other part of the molecule without hampering with the aldehydes or ketones that is in the molecule. So you protect the aldehyde or ketone using one of these reagents. This is actually a very popular one. Ethylene glycol is used for protecting, making an acetal. And then at the end of the reaction, you can hydrolyze this back to that corresponding fetal compound. Any questions?